Okay, so we're going to use a general waiting time strategy to model mutation and jointly estimate the tree shape and mutational process. So let's just talk about waiting times generally. So I've tried to come up with a good example for this. I don't know if I have, but here are a couple bad examples. So one would be, so let's go in, let's say every day you go in and you play 2 lottery tickets. So you buy 2 lottery tickets, and one of them has a chance of 1 in a million that you will win $100,000. And the other one is a more low stakes thing, and you have a 1 in 100 chance of winning. Okay, so every day you go in and you play the lottery. So most days you're not going to win, right? Because no days basically you're going to win this one, and only 1 in 100 are you going to win this one. And so most days I ask you how did it go, you'll say it didn't work. I didn't win. So it's a waiting process, and then the question would be, how long do we have to wait until you win one or the other of these? So we've already done something a little bit like this, right? Remember when we were talking about a coalescent process with 3 different individuals, we said the waiting time as we go back in time to a coalescent is the probability that these 2 coalesce plus the probability that these 2 coalesce plus the probability that these 2 coalesce. So that the rate, like the total rate, is equal to rate 1 plus rate 2 plus rate 3. And so similarly here, if these are our rates, then our total rate for winning the lottery would equal to 1 over 10 to the 6 plus 1 over 100. Okay, so in general, we have this idea that the total rate at which things are happening is equal to the rate at which each thing is happening. But we can go further than that. Then we can ask, given that something happens, what's the chance that it was the first thing or the second thing or the third thing? So we've already kind of done this intuitively in the case where we have either these 2 can coalesce or these 2 can coalesce or these 2 can coalesce, and each one has the same rate. Then given that a coalescent event occurs, we kind of have a sense there's a 1/3 chance it's this one, a 1/3 chance it's this one, and a 1/3 chance it's this one. But we can generalize that, and we can say that given that something happened, so if something happens, well, actually, let's call it an event. So if there's an event, so given that there's an event, and so we generally write given like this. So if we want to know the probability of something given that something happens, so the probability that it's the first thing that happens, given that it's an event, is going to be equal to the rate of the first thing happening divided by the sum of the rates. Right, so the total rate, or R1 divided by R1 plus R2 plus R3. Okay, so let's do this for our lottery example. So then that would mean the process that we're going to call this one R1, we're going to call this one R2. Then the probability, given that something happens, so the probability that it's the one, the big one, given that an event happens, given that you win, that one of your tickets wins, so then the probability of that is going to be equal to R1 divided by the sum of the rates. So this is very close to, since this number is much smaller than this number, this is very close to 1 over 10 to the 6th divided by 1 over 100, or 10 to the negative 4th. Okay, so in this example, it kind of makes sense, right? If given that you won a lottery, what's the chance that you won this one versus that you won this one? We kind of know if you come to me and you say, hey, I won the lottery, that the chances are much higher that you got the low stakes one than the high stakes one. And here we can formalize that and show, given that you won the lottery, the chance it's the high stakes one is around 10 to the negative 4th. So in general, we're going to use this in the next video to talk about, given that there's an event, what's the probability it's a mutation, what's the probability it's a coalescence.